Welcome to Finite Element Methods. Today we'll be covering springs, the energy approach. I discussed previously the equilibrium approach, but the energy approach is something that we'll be covering and we'll be encountering in this class. The theorem of minimum potential energy states that the equilibrium shape of a structure is also a shape that minimizes the structure's total potential energy. It only works for conservative systems. The deformation has to be elastic and there cannot be any Fowler forces. So again, if I'm able to calculate the potential energy for the system, the shape the structure is going to take is going to be the shape that minimizes that potential energy. That's what the theorem says. So typically the energy is written as strain energy plus the potential energy due to applied loads. You have to add the strain energy plus the work done by external loads, and minimization of this function with respect to the unknown quantities at the nodes renders the system in equilibrium. Because the only unknowns that you're going to have for the total energy, total potential energy, is the unknowns at the nodes. So if I minimize pi with respect to those quantities, then I can tell you how the system deflected. And to illustrate, in example number 1, say I have a spring, and the spring has a load applied P here. That load applied P will stretch that spring some amount, delta L. So then in that case, the total potential energy, and you should know this, the spring energy is 1/2 K delta L squared. That is the energy, which is the energy under this curve. Force F relative to delta L, that energy under that curve is 1/2 K delta L squared. That's the area under this curve. And that can be quickly derived if you're curious where that comes from, as 1/2 K delta L. That's the energy under the curve. I'm sorry, F. But F is K times delta L. So that renders this quantity there. And so what is the energy, the potential energy due to loads applied? Let's look at that one instead. The energy due to loads applied is just in essence P, how much this P mu moved due to that deflection here. So that's P times delta L. So total potential energy is this. So all we have to do then is we need to take this delta pi respect to delta L, because I don't know what delta L is. That's what I'm looking for. Because that's what the theorem says. The theorem says that those deflections that render the system in equilibrium are the ones that minimize the total potential energy. To minimize this function, I have to take the derivative of pi respect to delta L and set that equal to 0. And when I do that, I get this equation. That equation is the exact same equation you should get from the equilibrium equation that I discussed earlier that I had derived. It's exciting that we got the same thing using the energy method. And it should be exciting because it will be used in this class over and over and over and over. We're going to see that over and over and over every single time. For example, number 2, if I were to apply the energy approach, let's look at that one. I have for element number 1, for a local element, general local element, I have 1/2. The energy of that spring is this, generally speaking. So this is a spring. For element E, then that's the energy. And if the spring constant is E, that's what I get. So that makes sense. The only potential energy applied for the example problem that we had is this one. So the work done due to that load is P times D2. That load applied P times the deflection D2. That makes total sense. So that's what I have written there. And that's the energy of a single element. So for element number one, the global was D1. The local was 0. For DJ was D1. For element number one, this is 0 because it's fixed. So, and then the energy for spring number 2, if you go here, spring number 2 is D2 minus D1 squared, which is what you see there. So what is the total energy of the whole thing? The total energy I'm trying to clear this up so it's not too much information. The total energy then is the spring energy for element 1, spring energy for element 2, times the work done due to the applied load. And now pi depends on the deflection D1 and D2, which are unknown. So the deflections D1 and D2 that render the system in equilibrium are the ones that minimize pi. So the derivative pi with respect to D1 is 0, derivative pi with respect to D2 is 0. And now I have two equations, two unknowns. I should be able to solve for D1 and D2. So when I do that, the derivative pi with respect to D1, and I'll let you do that on your own, you will see that you will get this equation. And when you take the derivative with respect to D2, you get this second equation. So you get two equations. I can put that in matrix format, and guess what? That's the same thing I found using the equilibrium method, but I had to use code numbers back then. I didn't use it here, but it's the same idea. So this is how the energy approach works. The total potential energy is usually going to have a quadratic form. You can see here it has a quadratic form. You see here the deflections are squared. The energy for the system can usually be written in this manner. For a single element, it's going to look like this. And the global energy can be written as this. Once you get the global energy, you can write it in this manner. You can always write it in the way I'm showing you here. And it turns out that I can expand this, and I'll get this, and I'll get this, which is the same thing as this. So what I'm trying to say is this energy can always be written in this manner. And to get from here to here, the proof is very simple. Multiply the first row times this column, and you can see that here. Then multiply this vector times that, you get this. Then sum everything up, and then this becomes a square, which is the energy of a spring. We just said that pi equals 1/2 k delta L squared. This right here is delta L. So you can see that that's the derivation. That's the derivation for a that's a derivation of the energy for a single element. And you can see how that equation is correct. And that's why this is correct. If I make this K, I make this D transpose, and this is D. So if I take this equation, it turns out that I can add everything up, and the global energy is going to look like that. It turns out that if I differentiate, and I don't want to do the derivation here necessarily, but if I take that global equilibrium and I take this derivative with respect to these unknowns, you will get the equilibrium equations for the system. It turns out very nicely. And I encourage you to do this derivation with just numbers. So you basically can do, I encourage you to do this, for example. Instead of using summation, because that could be confusing, say pi is equal, and then do summation 1/2, summation, and then just do I equals 1 to 4, just randomly. J equals 1 to 5, just for fun. Sorry, just make it the same. 4. And then do D I K I J dj minus, and then do summation of I 1 to 4 qi di. And I encourage you to take the derivative pi respect to d1, the pi respect to d2, and so forth. When you do that, I guarantee you're going to get a equation, something that looks like this. It's better to do it with numbers so you can see how it works out. But here is the derivation with variables. In summary and review, I can discretize the body with spring elements. I can approximate the local element behavior, and I can write the energy equation for a single element, which looks like that. And then I can assemble the global equilibrium equations, which is going to look like that. And minimization of that is going to look like this. I get the same answer with the energy approach. Now let's take the example of a continuously varying. So what I want to do is now apply this to bars, to bar structure. So you can see how that works out. So here I have a bar, a structure that has aluminum and steel. And that's a discrete body because this is aluminum and that's steel. So it's kind of divided into aluminum and steel. But say you have the modulus varies like that with this equation, but the area is constant. How do you deal with that? So we can compute a spring constant from properties of a bar. The elasticity equations are that stress equals E, the Young modulus times the strain. Strain deflection, we all know that strain equals du dx. And you can derive that very simply by looking at the change in length. So what is the relative deflection that I have when this point moves to this point and this point moves to this point? Well, that's this minus that, which I get that, and that's divided by the original length, which is delta x. So change in length divided by original length, and that in the limit, that gives me du dx. So uniform bar with non-distributed load, say this is L, that length here is L. The strain is going to be delta L, the change in length divided by L. Stress is the force divided by area. But stress equals E over times epsilon. And stress is P over A. And epsilon is delta L over L. So I can bring this to the other side of the equation. So I get that. And I can call this whole thing my spring constant K. So a little trick there. And I'm able to turn now the bar problem into a spring representation. So that's how I could idealize a bar that has its properties. I can idealize it as a spring, okay, that has a spring constant K by using that formula. If I know the modulus, the area, and the length of that bar, I can basically come up with a spring constant for the spring. I covered it earlier, but I didn't explain the derivation. This is the derivation really quickly provided to you. So the basic FEA procedure, discretize the continuous body into elements, approximate local behavior, and then patch it together. That's what we want to do. So say that instead of a continuous, say I have a situation where I have a continuous distributed load Q. And it's fixed here, and I have a bar. How will we define K? How do we define Q? The modulus is varying, say. How do I go about that? I could use a 4-element discretization if I wanted to. I have a node 0 here, and I have a node 0 there on purpose. I have a, because it's fixed, so that degree of freedom is 0. And then I have degree of freedom 1 globally, 2, 3, and 4. And you can see it numbered there at the bottom. Globally speaking, I have loads also, Q1, Q2, Q3, Q4. Okay. But how do I define those? How do I define that load? How do I define that spring? Because in this case, the load is distributed and also E varies. How do I go about that? Let's create the code number first. I have for spring one, element one, I have 0, 1 because it's connecting 0 and 1. Element number two is 1 and 2. Element number three is 2 and 3. Element four is 3 and 4. That's a code number for that. I want to assemble the element local behavior, but before we have to derive the local element behavior. So one thing you could do is to lump. So for a single element, I have Q naught applied over the element, over the bar. What I could do is I can take that load and put some of it here and some of it in that node. That's what I can do. That's one approach. So I can take Q naught, the first Q naught, which is distributed over the element, and put half, maybe half on one side, half on the other side. For EX, what I could do is I could come up with some average value of EX that I could use to calculate the spring constant. That's one way. And this extra load that we're talking about here somehow needs to be added up to the element. You can see that here. That's new. I have to add a distributed load. Well, then it's going to show up here as you see. The rest is the same. These are the local internal forces. That's the stiffness of the element. This is the local deflections of unknowns. So it makes sense if the element length is LE. The total force is Q naught times LE. I'll put half of that here and half of that here. That makes sense. And because E of X varies, we can take an average over the element. So say this is I and this is J. I could calculate the midpoint somewhere here. So that will be xi minus xj divided by 2. And that'll give me an average value somewhere in between. So that's one way to define k, if the modulus vary like that. In this case, E can be defined for every single element in that manner. So now I know everything. I know k for every single element, which can vary, and it's going to vary according to this formula. And I know the loads that are being applied from here, which I'm putting some of it on this node and some of it on this node because I have a distributed applied load externally. Now we need to patch and assemble the elements together. For element 1, 2, 3, and 4, you can see the code number on the right hand side. I can now assemble the whole thing using, I'll do an example, 2, 2. I have to fill out 2, 2. Well, I look for 2, 2 here, it's not there. I see it here. I don't see it. I see it here. I don't see it here. So I can add those two together here, and that's what you see there. You have to just fill it up for all of them. Now we have to assemble the global forces. And by Newton's law, these forces here have to add up to the force externally. So the nodal load matrix is going to be consisting of external loads applied concentrated to a node and external loads applied from the distributed load to the node. So these are concentrated loads that I have. These are coming from distributed loads that I have. We don't have any concentrated loads here. If you look here in the example that we have, let me go back to the example. All we have is this distributed load. That's it. We don't have a point load anywhere. No concentrated load. It's all distributed. So for that reason, the concentrated force vector is going to be 0 in our example. And I'll use the same procedure. For element 1, I have 0 and 1. The local numbers, 1 and 2, 2 and 3, 3 and 4. Globally, I have 1, 2, 3, and 4. So I look for 1. I see a 1 here, and I see a 1 here. I don't see a 1 in element 3 and 4. So that means that element number 1, this needs to be added to that one, and I get Q naught L. And you can see that I can keep filling this up. Note that here L is L divided by 4 because I divided the domain, that domain I divided into 4 equal elements of L over 4. So small L is actually L over 4. And so that's why you see that here. So I don't have any concentrated loads. In this example, it's all distributed load. But I know this fully for the system. I know this fully because it's a distributed load. So I can now, and I know D1 is 0. So I can use the last 3 equations. Invert is going to be this matrix, by the way, when you do it. Invert K and then solve for D2, D3, and D4 for this example. In summary, I showed how to discretize a body where you have a distributed load and how to deal with that. I showed you that the modulus can vary and how to account for that in K, the stiffness matrix, and how to assemble the global equations of equilibrium for the distributed load as well. In Abaqus, the way you're going to implement this in Abaqus when you use it, what you see here is an input deck. This is called an input deck. You can actually do the whole thing writing everything down instead of using CAD. If I do an example quickly, the way it works, the first section defines the nodes, the next one the elements, the next one the spring information, the stiffness of that spring, and then the solution procedure. That's how this works. For the node, you're going to describe the node number, the x and y coordinate system. So here I just have this example here with 2 elements, and I put random numbers. I put a node value of 5, 6, and 7. So 5 is a 0, 0, and that's what you see there. Node number 6 is 0, 1, 0. I randomly selected that just to illustrate. Node number 7 is 2, 0. That's a format that you will enter it in. This is actually what's done in Notepad. So very, very easy, these 2 zeros, all right? And then you have to define the element connectivity, which I already discussed, the code number. So for element 10 is connecting nodes 5 and 6. Element number 11 is connecting nodes 6 and 7. So that's what you provide. The type of element in Abaqus is called spring 2. And I created a set. I just created a set because I like to have sets. So when you see 2 stars, that's a comment. So this is all comment and is ignored. A single node is a command, and star node is where you define the nodes, x, y, and z, the coordinates of that node in space. And a star element defines the type of element you're selecting and the connectivity of that. Clearly, element 10 is composed of 5 and 6, element 11 is 6 and 7. That's what you provide here, and you're going to provide it here with commas. And then spring, star spring, is where you define the stiffness. You can see here the 2 stars are getting ignored, so you can ignore all that. I'm taking this element set with spring, and I'm attaching the properties for all these elements by referring the L set here. And I'm only going to look at degree of freedom of the first node and the degree of freedom of the second node. Now, a normal node is going to have 6 degrees of freedom. 1, 2, 3, 4, 5, 6. These are translational, these are rotational. Because we're only looking at axial deflection, axial only. I only specified 1, and that's why you see 1, 1 there. You can see 1, 1 there. The stiffness that I chose is 10,000. And the static solution, I put 1, 1. We can discuss that later. It's not a big deal now. The boundary condition, node 5, we fixed it by specifying that degrees of freedom 1 through 6 of that node is 0. So we fixed that node. And a load, a concentrated load, star C load is applying a concentrated load. That's what that's doing. So a concentrated load was applied of 10 pounds in this case, or whatever units you need to be consistent with the units that you use. Star C load here is node 7. You can see that there. Degree of freedom 1 of that node, and then a load of 10. Okay. In the boundary conditions, what I did is I applied the node, what node number, and here you have to specify the degrees of freedom that are fixed, and then 0 is a value of how much is fixed, 2. If you run this in Abaqus, it's going to give you the spring deflection for these two elements, and I'm showing it here. Makes sense that you have 0 there. And the maximum deflection happens there. You can actually probe the values to figure out what is the deflection at, for example, nodes 6 and 7. At node 6 is 0.01, at node 7 is 0.02. You could potentially verify very quickly if you wanted to, and you will see that you'll get the right answers. Right, because the deflection is a load divided by stiffness. The load is 10. The stiffness is 10,000. So what do I get? I get 1. It's like a 0.001 for this node. And this is going to deflect an additional 0.001. So add this to that, you get 0.002. That's called a hand calculation. You check your analysis, doing hand calculations to make sure everything makes sense. So the way this works, you produce this Abaqus input file, and then you run the model. You basically run the model. You import this model into Abaqus and run it from there. That's how it works. I'll create we have tutorials on how to run these models, and you should be able to access them. There's some special cases where the deflections may not be non-zero. Right now, I made this 0, right? But if you have cases where this degree of freedom that's specified is non-zero, it's actually convenient. So I already discussed how to deal with when it's 0. But there might be cases where we apply a deflection that's non-zero. In those cases, it's better to actually put a number there. It makes the calculation a little bit easier. So here, what I've done is I've labeled this as 1 and 2 and 3. I'm calling this degree of freedom D1 and this degree of freedom D2. This one, the value is G, and it's non-zero. The element code number is so that for element 1 is connecting 1 and 3. Element 2 is connecting 1 and 2. And element 3 is connecting 2 and 3. And what I want to do in the global degrees of freedom are 1, 2, and 3. Okay. When you have a non-zero value of G is better a non-zero value of deflection is better to do it the way I'm doing it here. And you're going to then kind of put calculate k, right, for each element, and then you're going to assemble it. So in this manner, 1, 2, and 3. And note that G is non-zero, D1 is unknown, and D2. R, the reaction force, is unknown. There's no load applied at node number 2, so that's 0. There's a load applied here at node 3, that's 3, or degree of freedom 3. And now you can use the procedure we discussed before, where you partition the matrix, and the way you partition it here is like that. That's how you partition this to get in this format. And then you'll just follow the procedure we discussed previously to solve for D1 and D2, because you're also partitioning that into specified degrees of freedom and unspecified. So here U bar is this one, U is this one. And again, I'm dividing this in submatrices. Yeah, so now all you have to do is, you know, this KUU here. So invert that. You know Q bar, you know this whole thing, which is that. You know this one, KUU bar, completely. And you know the deflections that are specified. So you can calculate the unknowns here, D1 and D2. And then you can calculate the reaction forces. So that concludes the lecture for today, and I hope you enjoyed it.